At this point in the manual, we are really no longer introducing new instructions or elaborating on instructions that you haven't used before. Now we're moving into writing code, troubleshooting code for something more practical, a practical application. However, we don't have an actual machine or process to automate that's sitting right in front of us. If you have a job or a position where you're going to write code and you're going to download it into a controller on a processor machine and then commission it. Commission it means that you're going to run it, and then whatever it doesn't do right, you alter your code until it does do it right to the satisfaction of the person who has purchased the machine. We don't have the benefit of that. So instead, we have to use virtual processes, and virtual processes are made up of virtual devices. Now, the digital field device simulator that I'm using has 6 inputs and 6 outputs. However, the I/O module that I'm using, the combo 6 in, 4 out, is only connected to 6 inputs and 4 outputs. And we've, for the most part, stuck to that ratio and quantity of I/O in all of our manuals, because when you're working with licensed switches, when you get beyond 6 in and 4 out, it gets pretty tough. It becomes relatively difficult to keep track of which switch is which device input and which light is which device output. To increase the size of our virtual process or machine and reduce the complexity, we write code that represent virtual devices. In other words, in the first one we're going to do for a pneumatic cylinder, when you energize the solenoid, that solenoid valve, the electromagnetic force of the solenoid, pulls the spool or shifts the spool to shift where the pressure is applied to the cylinder. So if the cylinder is retracted and you shift the spool, it moves the pressure to the piston side and allows the rod side of the piston to evacuate the cylinder, and it extends, and vice versa. When you de-energize a single solenoid controlled cylinder, then a spring returns the spool in the valve, and now you're putting the pressure on the rod side and you retract the cylinder. Well, if you consider that behavior, that means you energize a solenoid, and after a period of time the cylinder is either extended or retracted. And we know it's extended or retracted either by virtue of a timeout, a done bit, if you're going to do timer-driven sequence, or a proximity switch, Hall effect sensor, but a sensor senses that the piston has moved to the extend or the retract position. A virtual device would respond to an output bit and feed you back an input bit to say that it did what you told it to do. Now, there is no real cylinder, so it's a virtual device or a virtual cylinder. So that's where we're headed next, and then we will use these virtual devices in a virtual process. We started out real simple, and we show the state of the extend solenoid. In other words, in the very first instruction it says true if on. If bit 0 is on of that output module, then we have told cylinder 1 to extend. Those of you that are more used to the older format for programming that was more true to electrical, you have to get adjusted to this style where we put loads in series. A TON instruction is normally considered an output type instruction, and that's simply because a time delay relay had a coil, but it had control lines that controlled how it behaved. In other words, once you energized the coil, contacts didn't close until after a time delay. And that's basically what you have here. But then, in series, after the normally open contact, if you will, or the true if on for the timer done, cylinder 1 extend time done, then we have another load. We have the coil for or we have a proc switch, but it looks like a relay coil. So look at what we have here. This is really simple. If the logic sees that you told the cylinder to extend, and remember, we don't have a cylinder. We don't have a solenoid valve. This is virtual. In your logic, when you turn on output 0, and it'll show up on your LED backed push buttons on your digital field device simulator, if that's what you're using, when that output comes on, it starts accumulating cylinder 1 extend time. It has a preset of 2000. Of course, everything in 5000 is 1,000ths of a second. So 2 seconds later, the done bit comes on, and it turns on another bit that simulates a proximity switch. In other words, the cylinder is extended. You tell the cylinder to extend, and 2 seconds later it says it's extended. This is a timed event, but what we're doing is we are simulating the proxies, because if you were out there on a machine, you probably couldn't see the cylinder anyway. Maybe you could, maybe you couldn't. And if you're in the manual mode and you tell the cylinder to extend, if it's buried deep in the machine, you wouldn't see it anyway. You might not even hear it. But these days, most cylinders have a minimum of 1 proximity position switch, either on the extend or the retract. It just depends on the machine safety. The machine's going to be more damaged if it extended and you didn't know it, or if it was supposed to retract and it actually didn't. It just depends on which end of the cylinder you want to put the sensor on. Personally, when I work on a process, I, for the most part, get right in their face that I want a sensor on both ends. What they'll do to save a few bucks is only put a sensor on one end of the cylinder. Now, in some cases, 2 sensors won't even fit on the cylinder. I've seen that hundreds of times where the stroke is so short or the space is so limited, you cannot put 2 sensors in there. This little simple rung here is energize the solenoid. 2 seconds later, you're simulating that the cylinder is extended. That's simple. The nice thing about virtual devices is the cost is minimal and space is abundant. So in my virtual cylinder, when I energize or set the bit local 1 O for output data dot 0, when I set that bit to 1, that means that I want the cylinder to extend. 2 seconds later, local 3I data dot 0 is set to 1, and that's my indication that the cylinder has extended. Now, if you look at the difference between those two memory locations, notice that I'm examining on an output bit, local 1 O data 0, the very first instruction. That's a literal memory location that's going to control the state of field wiring on an output module. But at the end of the rung, it shows I'm turning on an input. But if you look close, you'll see that's not really a module defined tag. That's one of the virtual tags that we created. See, it's local underscore 3.I.data.0. And that's because when I created the user-defined tag, remember over here, user-defined, that I could not, remember this, that's an input, I couldn't have local, this is the class of objects here. I just wanted to remind you where you created that. Now we'll go up to the main program, and I wasn't planning on doing this, but I started doing it, so I will continue doing it. And we have our tags right here, and evidently in the controller tags I moved these virtual right here. See, these are real tags. I mean, these are actual module defined tags here, and these are the instances of these module defined tags, okay, which are right here. These are the class of objects. You've got the analog card, and you've got the combo IQ6XOW4. So these are real I/O here, 1 and 2. But 3 and 4, notice instead of local colon slot number 1 or 2, it's local underscore 3 underscore 4. And then in here we've used these other user-defined data types to create these things that look close to being I/O. 3I, this is simulate an input. So we're actually turning on a bit that would simulate an input. Now you can't turn on an input in a real program where you actually have input modules. And this goes way back to the beginning in the first manual, where if you have, we'll just do it right here, data. Okay, you see that 4 and 5 are on there, right? And I'll go over to my switches and turn them off. These are real inputs. If I try to turn this input on, put a 1 in there, it's not going to take it, simply because I put it in there. It may have actually gotten into memory, and it may have actually changed that memory location for about 100 or so microseconds. But because you're updating the state of those bits from the real input modules, 5-6 times every thousandth of a second, you might as well say it just didn't change. Okay, so that's a little bit of review, just in case you've forgotten some of the things that we talked about in the first manual, Volume 1 or Beginner. This is Beginner Plus. Okay, here, if I energize this and I will turn on that output, I don't have logic to turn it on, because remember, this is my virtual cylinder. So when we write logic, and in our logic we energize that output to extend the cylinder, that logic will turn this bit on. Right now we don't have any, so I'll try toggling it, and see after 2 seconds it says it's extended. If I de-energize it, then watch the second rung. When you de-energize a solenoid, then 2 seconds later it's saying it's retracted. So basically your virtual cylinder does nothing more than give you 2 bits that simulate proximity switches or sensors sensing the piston. 2 seconds after you told to extend, it says I'm extended, and 2 seconds after you de-energize this single solenoid, 2 seconds later it says I'm retracted. And that's as much as you can get from a cylinder on a real process, as you tell it to extend, and then you're waiting for the input from the proximity switch to say it's there. Then you go on about your business, and then when you tell it to retract, you turn off that output because you want the cylinder to retract. The valve spool shifts, pressure goes on the rod side, and it starts retracting, and 2 seconds later the piston is sensed by the retracted proc switch, and that comes back into your controller. That's it. That's a virtual cylinder right there. And we could add some more things to make it more clever, or to put diagnostics on it, but for right now, that's your virtual device. To make the code a little bit more tidy, clean, we combine the 2 rungs into 1 rung. They still execute exactly the same, and probably doesn't require any more execution time than it did when it was 2 separate rungs. All that we did was combine the retract delay into 1 rung with the extend delay to keep it as one piece of logic so it doesn't get separated. Whenever you do logic that's this interactive, it's better to make it 1 rung so no one accidentally moves 1/2 of this somewhere else in your program and you lose track of it. That's all we did with this last little step. We changed a few things in the next couple steps. One is because of the way we're going to control our virtual machine, we're going to extend and retract cylinder 1 and cylinder 2 with the exact same solenoid valve. So here we have 2 rungs, and I will make this a little bit smaller to get them both in there. So you see these are 2 identical rungs. Now I'm going to bump this back up so it's easier to read. So you see we're taking output 0, true if on, true if off, true if on to extend, true if off to retract, true if on to extend, true if off to retract. So these instructions address the same memory location. So we're operating cylinder 1 and cylinder 2 with the exact same output bits, or bit. But we have 4 separate timers. Cylinder 1 extend time, cylinder 1 retract time. Cylinder 2 extend time, cylinder 2 retract time. And then the done bits, of course, are operating these virtual inputs. Cylinder 1 extended, retracted. Cylinder 2 extended, retracted. What you did was you took this rung of logic, you changed the tag name that aliased this to cylinder 1, cylinder 2 extend. Then you duplicated this rung and created 2 new timer instances of timer data types, and you changed the tag names on all these instructions to match. That gave you 2 cylinders. Then you did the same thing again for 3 cylinders for cylinder 3, only this time you're using an output bit and it only controls this one cylinder, cylinder 3. Same thing for cylinder 4 and for cylinder 5. That was all that you did, was duplicate logic that you already understood. So now you have 5 virtual cylinders. This is our virtual machine. We have 2 conveyors, and those are illustrated by the 2 gray rectangles. One is vertical and one is horizontal. We're looking at the top view of the process, and the process begins with the green call out, raw stock from upstream. Now this raw stock, it really doesn't matter what it is or even what shape it is. It's just raw stock. Now in our case we're doing round pieces of material, and I have a blue one and a red one. Colors are irrelevant, just to make them stand out a little bit, and they come in on the conveyor from upstream. The first thing they really encounter, even though they do move into the scan zone for the barcode reader, your system, our control system, does not sense or know anything's there until number 1. PE1 senses part. So when that part interrupts the optical path of photo I1, then our system basically says, aha, we've got a part coming in. And from that point on, nothing else can happen unless you turn on something. Now in this case, the only reason that we're sensing it there is because we want to read it with a barcode reader. Now, we want to see the part number on this to see if it requires the operations on it that it would receive at this workstation. So if it is the appropriate barcode reading, then when it gets down to photo I2 and breaks that optical path, then cylinder 2 will extend to push it into the workspace where you see the drill motor and cylinder 3. Now cylinder 1 and 2 are going to extend together. So if you go back to number 1, photo I1 senses part. Number 2, barcode red. Now you're looking for number 3. Number 3 is PE2 senses the part. Number 4 is cylinder 1 and cylinder 2 extends. Okay, once they extend, cylinder 1 puts a stop out there so another part coming from upstream can't interfere with the process. Now we're not considering another part coming into the barcode reader while you're running this one part. That's a convolution in the process for a later point. And remember, at this point in your learning process, we encourage you to kind of go off and do your own thing. But if it doesn't work out for you, then you need to come back exactly to where you departed from and do it the way we say to do it. And then again, if you feel more adventuresome and want to deviate off again, remember, this is your learning experience, so you do it any way you want. Okay, so number 3, we sense the part. And if the barcode was appropriate, then cylinder 1 and 2 extend. If it wasn't appropriate, it keeps right on going on the feed conveyor, not off onto the floor, but on downstream for something else. 4, cylinder 1 and 2 extend. And of course, number 5 is going to be that prox 2 end of stroke for cylinder 1 and cylinder 2 sense that they're at the end of stroke. Because we're not going to do anything until we sense, in the case of cylinder 1, the stop being all the way out there, that's not a huge concern. But cylinder 2 fully extended is pushing the part into that workspace against a V-block, on the other side of which is a drill motor with a drill bit, or a drill as they say. We want cylinder 2 fully extended and holding that part against that V-block so we can drill a hole in it. And of course we also want to know that cylinder 3 is not extended because we don't want to push the part in there. There's a lot that goes into it, but the point is, number 5, we're at the end of stroke for cylinders 1 and 2. And then we look for another action. So the orange are the actions, the blues are the feedback, so to speak. We had oranges of extending cylinders 1 and 2, and then 5 we had blue, prox 4 and 2, end of stroke. And then 6, we turn on the drill motor. We just turn it on and let it get up to speed. And then after it gets up to speed, we have another action, and that is we tell cylinder 4 to extend after a 3-second delay. We want the drill motor up to full speed before we run the cylinder into the part. At number 7, cylinder 4 extends, so what would you look for as the next step or condition that we're concerned about? Well, if we're extending cylinder 4, we want to know it extended. So number 7, cylinder 4 extend, then you just look at the extend prox 5, and then look, oh, that's number 8. Prox 5 sees that the cylinder is extended. Now once it's extended, then we need another action. So 9, once it's extended, 8, prox 5 extended, 9, cylinder 4 retracts. Now we may want to put a delay in between 8 and 9, meaning, remember that these proximity switches, Hall effect sensors, whatever they are adjustable, meaning that you can adjust them at the ends of stroke, retract and extend. They just go on when it's fully extended and fully retracted, or maybe it goes on before it's fully extended and retracted, and there's a little bit more motion there. In most cases, you want to add a little delay before you say it's actually extended or retracted, just to make sure it is, based on who installed these sensors on the cylinders and how they adjusted them. You'll see this out in the field. When you're commissioning a project, you will spend a lot of time fooling around with adjusting the physical location of sensors, photo eyes, proximity switches, limit switches, you name it. Okay, now we want cylinder 4 to retract. Well, if cylinder 4 is going to retract, the next thing we should see is that it's retracted, which would be prox 6, which you see right almost below number 9. You see number 10. Prox 6 has retracted. Now, we don't need a delay there, because whether it's fully retracted or only partially retracted, we're then going to probably do another little delay. Another reason for delaying the extend, going back to number 8, is if you have done a lot of hand drilling, you know that it takes a few moments for the drill bit to auger out the debris, like a screw conveyor, an auger. It takes a little while for it to clear the debris out of the hole, so you want to leave it running. And then when you get back to the retracted position, you may want to let the drill motor continue for a little while, spinning the bit to cool it off. Because remember, it acts like a centrifugal fan somewhat. So it cools off the bit a little bit to leave it run. These are just all little fine things that you can add into your program on a more practical basis. Okay, so we retracted cylinder 4. And after we've let the drill bit run for a couple seconds to cool it off, then we turn the drill motor off. Well, the next thing after 11 is 12. So if you look around on your chart there, and I always have to look, then we turn the drill motor off. That's an action, and not all actions, like drill motor off, we have no way to know it's off, so we're not looking for feedback. Now, you could put a centrifugal switch on the motor, and when the motor comes to a stop, the switch closes and says it's no longer rotating. But we're not, that would be a waste of time and money to add that to this kind of process. So number 12 turns out is another action. And that other action is that we're going to retract cylinder 1 and cylinder 2. So you see, number 11, drill motor off, but also number 11 is cylinder 1 retract, cylinder 2 retract. So we have 3 number 11s. And there's no reason when we turn the drill motor off not to include that with telling those 2 cylinders to retract. And then, of course, after 11 comes 12, which proxies 1 and 3 says, okay, those cylinders are retracted. Now, we have a finished part in the workstation there in front of the drill motor. And we've retracted cylinder 1, but really specifically cylinder 2. So the part is no longer held there. So now we want to extend cylinder 3 to push that finished part out onto the finished product conveyor. It's got a hole bored into it now. So it's finished in this station. Now, that may not be completely finished as far as manufacturing goes. We don't care. This is just a one operation here to keep it simple. So cylinder 3 has to extend to push that part out onto that conveyor. And then obviously after 13 extending it, 14 is prox 8. It's extended. And then 15 is we're going to retract cylinder 3. 16, we see that it's retracted, prox 7. And then 17, we're going to turn on the finished product conveyor to move the part out of the end of stroke from cylinder 3 to make space for the next part. Then 18, since we turned on the conveyor, the finished product conveyor, 17, 18 is that part travels down on the conveyor and it breaks the optical path or blocks the optical path of photo I3. When that happens, then we extend cylinder 5 to hold the part there. Now, when you get further into this process, whether or not you extend cylinder 5 will really depend on what you want downstream. Maybe you just want to let the part keep on going, maybe you don't. But in this case, we're going to stop it. So we extend cylinder 5, and of course 19, extend 5, 20 is prox 9, it's extended. And then we turn the conveyor off because there's no reason to leave the conveyor running wearing any finish off the bottom of that part. And that's basically the end of the process right now. There's a lot more to it than this. But this is sufficient to get you going. And you see the 5 cylinders there, cylinder 1, 2, 3, 4, and 5. You've already created the relationship between the single solenoid that tells them to extend and the time delay before it says they're extended or retracted.